And welcome to Codebase Alpha. This is another special episode with Mårten, aka Fuel Snable from chat, and we're going to be talking about shaders. So last week we actually created our first shaders, and it was quite an amazing kind of process. Dragon and I, welcome. I'm glad you can make the stream. Let's without further ado, let's pop over into the code. I've got the shader we did last time actually running. And let's say hello to Mårten.
Hello there. How's it going?
Yeah, it's good. So I'm still fascinated by this this shader we've got here. It actually looks really good in the small window at the top here. It's very kaleidoscopic. It's a bit chunky, I guess. That we could do some refining in terms of the size of the lines, but it looks really, really good in that corner. So it's very psychedelic. I think it said last it's like a 1960s spy movie. Hypnosis machine. So
yeah, that was kind of what we want to achieve, right, with the kaleidoscope thing. And once again, this is just distance functions we are viewing, and with some post processing and things like that.
So we're in kind of I think we've got here 100 and something lines of code. Some of it's just kind of reusable functions we've created for creating squares and rounded boxes and circles, and we got the to and from polar coordinates kind of functions we got in there, but the actual meat of it, as you say, is this distant function df. So the kind of power of the distance function, and we're going to probably explore that a bit more either towards the end of this stream or in the next stream where we look at 3D and ray marching. But what have you got? I'll stop this because it's hypnotizing me. What have we got? What have we got planned?
Popping the LSD pills.
Yeah.
So no, I thought, well, this is kind of cool looking, right?
Very.
So why don't we put this on ShaderToy site so we can share this with people, and then we can maybe make our own web page. I'm not sure this is good splash screen for Codebase Alpha, but maybe you can squeeze it in somehow.
You never know.
Because what's cool about shaders is that because of WebGL, we can use this in our web pages, and I can look amazing because I know nothing about this React and Angular and all this kind of technology, but I can make shaders so people think I'm good at web, even though I'm not good. I can just open a canvas and draw some shaders. But so I thought we could try to do that if you want to.
That sounds good.
So why don't you go to the ShaderToy site and sort of I've been thinking a little bit myself with that thing, so I can show you what I did. That I kind of tinkered with this shader we created, and I put that on ShaderToy, and hoping that I get some positive feedback. Well, I wasn't surprised. I got 2 likes, I think, and that was pretty good because most of the shaders are like 3D and quite amazing, and this is just. Yeah, so not a go top, but I shared a link with you in this CodeShare.io.
Let's have a look at that.
So this is what I did before the stream. So I was like listening to psychedelic music and do this stuff. Hopefully it works.
Oh wow!
Yeah, so if you make this full screen, I think it's going to look quite weird. The compression, sort of, this is not it looks quite amazing actually on the stream.
It's phenomenal.
It's like universe kind of thing. Like you're sitting here at Codebase Alpha in this psychedelic universe. Doctor Who, I don't know.
Yeah, absolutely. Yeah, very much so.
Yeah.
And you can see it's based upon our design, isn't it? You can see that.
Yeah, absolutely right. And then I applied sort of some kind of Möbius transform to this thing to sort of get it to sort of be endlessly repeating and whatever. But let's try to make the one we did last week, and we can create our own sort of, ShaderToy and sort of share it with people and see what they think.
Cool.
Boy, the artifacts is really amazing.
Yeah, it's incredible.
It looks quite cool, actually.
Yeah.
So, in order to do so, you need to sort of create a user here and here you see the source code, by the way, on the right side.
Yeah.
This is how it looks, and it's basically what you had, but with some more space warp thing and the colors, and it's not that much difference. It's a little bit different. So if you click sign in the top right corner, and I got 2 likes as well. You see that?
Yeah, that's excellent.
Um,
I'm not seeming to get any control here. Let's have a look. Sign in.
Can I click it?
Oh, I think maybe we have to accept that. No, we had to accept the cookie thing. So I'm going to create an account.
Yeah.
Oh, we'll call it SMB.
So this is how I spent my whole last summer, doing shaders on ShaderToy.
I can see how it would absorb all your time.
Yeah, it really can, and you know, sometimes I almost think I also learn something, so it's not too bad. 92 plus. Oh yeah, okay. I have to do the computation as well. That's nasty.
Mm-hmm.
One more thing. Okay, we sent you.
I'll have to go and get my email, so I'll just do that.
But this is basically it's quite. I think it's quite simple setup to do this, and then you have a ShaderToy account. Then we can log in using a shader account, and we can create your own shaders. And it's a very simple process, I think. And the editor is not that bad. It's just that Kodelife is so much better.
Yeah, because the instant feedback, isn't it? That's what's great about it.
Well, is this 44 times 81? What are these? That's hard.
Yeah, get your calculator out. So we've got to wait for this this email to come through, and it's not come through yet. So we might have to kind of pad this bit out while we get a Oh, hang about, something's come through now. No, not yet.
If you log into the website, sometimes that goes faster. It's crazy. Yeah, dragging. It's trippy. This is, you know, it's a cheap trip. Well, it's not cheap. When I think about it, the computer is quite expensive. But, you know, and it's expensive trip. So
let's check our junk. Check our trash. Actually, it's a good idea to check our spam.
That's usually where my boss's email ends up. Yeah.
That's always good. That work emails end up in the spam folder.
Yeah.
Nothing there yet.
What if you take your username and password and try to sign in?
Here we go.
What did the site say? Username must contain. Yeah, it probably needs to activate it, right?
Yeah, I think so.
Oh well. So I got contacted by a guy, by the way, to tell you a story while we're waiting. Called what's called Man of Stick is his name. He's pretty cool developer in the F# community, and he always tries to optimize things. And he's on this quest to optimize link now. And he usually takes on these enormous tasks, which I'm quite admiring for doing that, because I think that's pretty cool that he does that. And I usually try to sort of, you know, come on, this is good work you're doing here. But I'm in my head, I'm thinking, oh boy, getting this PR through, it's going to be so much work.
Absolutely, yeah.
Because he really tried to optimize the core part of like link or, you know, F# and these kind of things. And that's hard because it's dangerous. But I mean, it's good that he tries to do it. So now we try to sort of create a better link that you can use as a drop-in replacement for link, but should perform better.
Right. I wouldn't even know where to start.
Do we redo the?
Do we try again? Shall we?
Account, yeah. One way to sort of make link faster is to sort of, you know, try to sort of build an abstraction so you can actually push values through the pipeline rather than pulling them, because that's yeah. Ooh.
Also, make sure I get it right. That's all. 168. So yeah, so it looks like it knows about us.
Yeah.
Doesn't bother sending an email.
That's a bummer. Because I wanted to show you the process of sort of converting this into something that's compatible with WebGL, because WebGL is a little bit different than, but we can actually start that, I think, anyway.
Yeah.
If you click new, but we can't save. But we can save in a text editor.
It's very strange. This website is
they are good at shaders, these guys. They're not so good at doing websites, I must admit. If you refresh the page, maybe if you use Chrome, sometimes it's worked better.
Tell you what, we'll try. We'll try Chromium Edge.
By the way, when it comes to shaders, now you can click the accept button. Hopefully, yeah, that looks amazing. The one-way trip. Oof. That's where we want to end up.
I can't click accept.
I click it.
If you can click it.
Maybe if you remove my control, so we don't have shared controls.
Yeah.
That worked, right?
That did, yeah.
Yeah, okay, amazing. Oh well, I learned something.
I'll keep an eye on the email.
Here's your first shader. We can't save it, but what we can do is try to make. You should remember this, but take the code we created, right, and put it above the main image function.
Okay.
And then we're going to rewrite our code so it fits into this. So it becomes ShaderToy compatible.
Do we need the version?
Sorry?
Do we need this version?
No, you should start from float the circle and below.
Float the circle, right.
And you see the main functions looks a little bit different here. So if you take the signature of the main function below there,
yeah,
and replace yours with that signature instead.
This main image one here.
Yeah.
Like that.
Because we supposed to return a frag color and we get the frag coordinate as an input here. So now we can remove the main image there, down there. We don't need it anymore. We need it for the signature. And then you take. It's not going to work correctly, but you take frag chord instead of in data vtext chord. So you take the frag chord there, right?
Yeah. Okay.
And I'm going to cheat a little bit and look at how I did it. I think this is the way to do it, because there are some slight differences. Can I have control?
Yeah.
Oh no, I can't copy paste. I never learned that. Okay, but I share some code in this code share thing here, and you can take that code and instead use that as the way to compute UV.
Right. Okay, so we're over here, aren't we? There we are. So UV is that. So we're going to
remove these two lines. Yes.
Do that.
Yep.
Okay.
That's good enough. And
just try
to compile this thing here now. You hit the play button there.
Okay, so we got time undeclared and clamp no matching function.
And that's because time in here is called iTime for some reason. So you replace time with iTime, capital T. Try to compile again, see what happens.
That's good. So it's clamp.
now it complains no matching overload, and that's because in WebGL we have to use decimals rather than integers, floating points. So you have to type 0.0 and 1.0.
Okay.
Yeah, exactly right. It's much more strict on these things.
Okay.
Okay, that seems okay. Let's scroll down.
Oh, some more right down here. Okay.
Yeah. When you see tau divided by 30, then you put in 30.0.
0.0. Okay. Yeah.
Yeah, 0.0. Yeah. And
that's high time here.
Yeah.
And
then tau divided by 7 is the tau divided by 7. Yeah. Okay. So this is, it's not that hard, but there are some things.
There we go.
Amazing. And now if you just had that confirmation email.
I'm just checking now. You'll think, yeah. It's gonna deliberately not send it or something, isn't it? Or there's gonna be something that's not right and it's not gonna send it through to us, but it's already taken our username. Might have to create another one. Okay. Mind you, the email might be used up as well.
Yeah, that's a bummer. Well, at least we converted it to WebGL. Okay. Copy paste these codes, we don't lose it. Because what we have now is code that we could use in our web page. Now, save it here, right? Where did it edit go?
So I've got it in my in VS Code over
good.
here.
Okay, good. By the way, there is a GLSL plugin here for Visual Studio Code, so you can get some nice coloring.
Yeah, GLSL.
Lint, literal.
Lint.
Lots of linting.
Syntax highlight of shader language. Is that one? That one?
You can try that. It was the highlighter. Yeah.
So we need to save it. What's the usual extension for? Is it GLSL?
GLSL.
GLSL. Okay, let's save this into our area, our GitHub repo. Well, our Git repo.
Well, I guess a stream, it should never really go 100% on a stream, right? Things like fail to register an account, that seems like a reasonable failure. It might be that this, what plugin do I use? By the way, let's see if I have some plugin here.
I was wondering if there's anything in here with a GLSL, but there isn't. We'll save it into there. There we go. It's nicely highlighted now.
Yeah, looks good, right?
Yeah.
The Kodelife is better, but this is, at least you can get some nice highlighting here. So this is good. So I guess what we have to go a little bit further in what are my plans, but so instead we make our own web page. So my suggestion now is my goal now is that we create a web page where we have this weird stuff playing in the background.
Yep.
And one way to do it is that we fork the repo I created, which contains, among other things, the SMB things we're having.
Sounds
good. So this is the one. So you might know it or not know it, but you can create a repo that is called, in this case, mrange, that's my name, and mrange.github.io. Then I get a site on mrange.github.io, and so I can just check in code here, and then that gets automatically deployed as a web page. That is a simple way for me to host these pages.
Right.
So in your case, you could create this as whatever your name is on github.github.io, and you have a web page for that thing.
Okay,
but that's important. But I think we just clone this repo for now. and run locally. Running locally is a little bit tricky because is that the background on the...
Yeah, it's my background, yeah.
Wow. It says unknown. What does that mean? Oh, okay, we have to go in there, right? Yeah, okay.
Yeah, that's a posh kit, that.
So, and so I have a lot of weird stuff in here. I do weird stuff sometimes, like physics and these kind of things. But let's go into diversion. That's another topic, talking about simple physics engines. That's if you're interested in that. I have a car simulator here.
Oh, right, do you?
It's in JavaScript. And the word simulator here is in citation marks, or
quotation marks.
Quotation. But I think it's pretty good for the amount. So if you have SMB2, that's your that's the electric ALF. So if you go in there and you take dir, and then you have the SMB image and index HTML. So if you open index.html in a web browser, if you type index.html, perhaps it just opened it. I don't remember.
No.
It's
okay.
If you type Explorer and space dot, so you open this page here. And if you double click the index, what happens?
There we go. There's good old electric ALF.
Yeah. Now let's look at it for a moment. I need to sit on a stream. It's so nice. Yeah. This is by the way, this electric thing is using some special technique we compute kind of clouds, but 2D clouds, and then we invert it and add a number to it, so a gradient to it. And that means that some points will be 0, and those points are the points where we see it looks like lighting. But the cloud you can see sort of waving outside this thing here.
Yeah.
So it's actually a shader that kind of computes a 2D cloud and then invert the cloud, to create this effect. It looks super nice.
Yeah.
I think. And
I'm just going to take it off because I think Dragon Knife, you're seeing in chat. I think that degrades the stream quality quite a bit when we have that full stream. So we don't have it too often.
Not on my machine. It looked amazing.
Yeah, it looked good for me as well. But I don't know if it's only on recordings. It seems to make the thing pixelate quite a bit. But yeah, it looked fantastic.
Yeah, I mean, no pain, no gain.
Absolutely.
Yeah. So my proposal here is that we take this thing here and we modify this example and add the shader code we did here. So if you open up this folder in, for instance, Visual Studio Code, we can have a look at how this thing is built up. You see, it's not that much. It's an image in index.html and some WebDriver JS thing. That's actually all there is. There's no other dependencies than that. Because I don't know how to do Java, I don't know how to do web development, so I do simple stuff.
Absolutely.
Yeah, so this is a basic page, and I have a special style here to sort of make sure that we have the canvas is sort of fixed, becomes fixed in the background. This set the index -1. If you scroll down a little bit here,
right? Yeah.
And here's a shader. So you see the script shader fragment. So this is the shader.
Oh wow.
Yeah, and we're gonna keep the prelude. The prelude is needed for setup, but the rest under the prelude. Under prelude, it should just work. Copy paste your shader in there. It should just work. Citation mark, quotation marks, again, and then in the end, and then you see it's not that much code to do the electrical.
No, there isn't.
And then we have below the fragment shader. This is a fragment shader. So if you scroll down a little bit, we have what's called a vertex shader. But we don't really do any vertex shader. We just pass it on. So the vertex shader is to sort of transform the vertexes, but we only have 4 here, the 4 corners of the window.
Yes.
Nothing to transform. And then we have call a start function that starts everything. And then you see they have the image ID SNB, but it's hidden. And then we have a canvas with a special class GL. So if you open the WebGL.driver here, we can explain that a little bit, how that works. So, okay, I'm gonna say I am not a very good JavaScript developer, so I just hack this together to make it work. It works. I'm satisfied. So don't look at this code for inspiration how to write good JavaScript, obviously.
You don't look at me if you want to write JavaScript, I must admit. So I'm just a beginner at JavaScript. I leave it to people who know what they're doing with that.
Yeah. So, but if you scroll down here a little bit here, so you have the start function. What the start function does, which is important here, is that it at line 49 it locates the canvas.
Yeah.
And so we have the canvas now, and using the canvas, we have an init function which I forgot where it is. If you scroll down down here, init WebGL is the function.
Yeah.
Somewhere. Let's see what that does.
Here it is.
It does something that's very simple. It says that get context experimental WebGL, so that then it tries to ask the canvas for a WebGL context. Now this should say OpenGL2 instead, but this works. So GL now is a WebGL context that allows us to draw graphics using WebGL, and ultimately to draw graphics using the shaders. So if you scroll up again, so what we do from there is, like you see, using GL, we can say clear. We can clear it.
Yeah.
That's create a background color. We enable depth. I don't know. I copy paste all these things here.
Mm-hmm.
You need the shaders. A lot of copy pasting. We have a texture that I created line 78. Create texture that loads the texture that we had in the SNB texture. We don't need it, but we leave it for now. And then we start the animation by setting this timeout, so we get a callback function every few milliseconds to sort of draw the picture.
Okay, right, yeah. Straightforward.
And if you scroll down a little bit here, so give it some overview here for people that's interested. So in order to sort of do this, we're gonna draw two triangles, or maybe it's a quad. I don't remember. But in order to do that, we need some vertices. And so we create these vertices at line 113. It's really stupid. It's just the different corners.
Yeah.
Like this is two triangles. So it's just we do two triangles to draw a box, and that is, or not a box, a square.
Yeah.
And then we have to do some binding. This is, if you know WebGL, this looks exactly like the C code. And we create a normal buffer, but we're not going to use it. We create the buffer data, scroll down a little bit here, and so on and so forth. This is just, but I just copy pasted all this code from someone that knew what they were doing. The good thing here is, like, after this is done, you don't have to change it. This is like static for everything.
Okay.
But I wanted to find a place where we initialize the shaders. So if we scroll down a little bit further, and I think that might be. Our draw scene is good. Let's look at draw scene, and then we can go back to other code. So what the draw scene does is that it loads these vertices, the vertex texture coordinate buffer. It loads the normal, which contains nothing, and it loads the shader programs at line 226 and 227.
Yeah.
Then here comes an interesting thing, which you might enjoy. Now, you remember we talked last time about the uniforms were the input parameters.
Yes.
Shaders. Here is what we're setting them.
Okay, right. These ones here.
No, the two lines above it.
These ones here. Yes, of course they are. Yes.
So first we get uniform location for eye resolution, which is defined in the shader.
Yes.
And then we set them to width and height of the window. Yeah. And then we have the time, which we continuously increment. So this is giving input to the shaders.
Yeah.
And then we bind it, and then we draw it using these draw elements. And that's just draw triangles, and there are 6 of them to create 6 vertices to create 2 triangles, and done. That's kind of what this thing does. So if you're used to shader code or like WebGL, this is very how it looks, and you can look at documentation, and it kind of matches the C documentation quite much.
Yeah, so I think in the last stream we looked at a learn WebGL or Learn OpenGL site, and it was. This is very much what they were doing on there. It was all these creating the two triangles, and this. I remember now these binds.
Yes, but what I want to do, and what you want to do, I think, is just we want to sort of get our shaders. We want to get whatever this we need to be able to draw our shaders, and then we don't care about this code, and at least I don't. So let's see if I can get our shader code to work here, right? So if I was saying was true, if you look at index.html, it should be, we should be able to take the shader code here from the end of the prelude to the script end, remove that, and put in remove my creative.
From 66, yeah. This lot here,
yeah. Yeah, remove 58 as well. License is not applicable here. Yeah, and we remove that. And then we go to the shader code. You save it somewhere.
Yeah, here it is.
Copy paste that. And it might fail, but I don't think it should fail too much. Hopefully not that much. Save it. What happens if you reload this thing in the window you had?
There we are. Worked first time. There's a bit of an artifact in it, but other than that, it's.
I need to look at the window here now. I'm waiting for the stream. It's not too bad, right?
Just needs scaling a bit. So there's a bit of an artifact in the horizontal plane there, but it's pretty good.
I don't see it.
No, maybe you can't see it. Then that's great. Maybe it's just
interesting. Wow. Let's ignore that for a moment.
It looks like it needs scaling down, doesn't it?
Could be. Yeah, it looks like the resolution is a little bit poor, perhaps. This is often a struggle to do it correctly, to find the proper resolution. But I mean, not too bad for the first try, right?
Yeah, it was brilliant. All we need is some rotating flaming skulls, and we're right back in the 70s here.
Yeah. So let's look at the resolution. If you go back to the WebGL code we had there.
Right.
The WebGL driver code.
Okay.
And if you scroll to the top, I believe. Scroll to the top. You see, I tried to tinker to get to the max width here. So, but
yeah,
that's your resolution on the screen, or?
It is, yes. 1920 by 1080.
Sometimes it's interacting with this. Yeah, whatever. It can also be if you zoomed in. I'm often zoomed in the browser.
Oh, we might be zoomed in, I suppose.
So if you look at it,
we might be.
So if you look at the zoom setting, I think it's the properties on the top right corner or something like that.
We're at normal zoom, so.
But so so using this thing here now, you can actually take this and put this on your web page, and have a WebGL thing, rendering it. It's actually kind of that hard. In addition, you don't need this texture. So let's remove the image here. So if you take index.html,
okay,
and then you go to bottom.
It's amazing. You just paste the code in there, and it all just works.
Yeah. So I tried to create this thing so it's as compatible as possible with simple WebGL ShaderToy. So it should just be for most things, not always. But so if you remove this image here, that is the texture, and then we need to change the WebGL code, WebGL driver. It's not that smart, you see. It could be smart, but it's not. So if you search for texture 0, I believe is the name. Texture 0. Yeah. So if you remove that thing here, and then we're going to remove everything that initializes and uses this. So we don't lose this thing, yeah. And then we don't bind it either. Bind texture. Yeah, okay, let's see now. No, let's go back here. Let's go undo it. Again. I see. Okay. Search for bind texture. Boy, getting this code right is a lot of tinkering, I can tell you.
Yeah, I bet. So
yeah, and then you remove this, the binding there.
That one there.
Not that one. No, but the one you had before.
That one there.
This one, you remove this thing, so we don't bind. So this is what binds the texture to the uniform sampler 2D, which is the texture.
Right.
I think it should just reload now. Try what happens.
Still seems to be okay.
Yeah, so now we remove the texture. We didn't need it. So why do it? So yeah.
Yeah.
You can show this to the web guys at work.
Yeah.
If you have one else and say, yeah, beat this.
I can see the new background to our new website. So yeah.
Yeah. You can put this in the background, like always present, and like, and then they go, oh and ah, you're a web developer king. Yeah, sure I am. Yeah, that's how I try to get some credibility in my web development skills. So, how did it go with the ShaderToy? Did we get the?
Let's have a look, see if we got anything. Nothing. Nothing in my inbox, and nothing in.
Blacklisted on the site. They know.
Let's go back and see what we can do. No, we got it saved.
Yeah. SNB2.
Yeah, let's try create another one. Yeah, just see. But it might be that it wants. Let's create Codebase Alpha.
Oh yeah, that's a good idea. What is that the same, or is that something else?
It's the same. It might complain.
But maybe it's the email that is the problem.
Could be.
What? This is crazy. This.
190, isn't it?
No, but it doesn't say.
Oh, it's times. Blimey.
Multiplication.
Where? 81 times 89.
I guess most people say, well, usually you have a calculator on a computer. This is actually the opposite computer test, because a human wouldn't make this. Then maybe that's the thing. If you enter the right number, yeah, the email was registered. Right? Isn't that right? I mean, if you're able to calculate this correctly, you're a computer, not a human.
That's right. Yes, it's not a very good test, is it? You need something that only humans can do.
You enter the wrong number because a computer will enter the right number.
Yeah. Let's see if we can get a password reset.
Yeah, that's a good idea. Introduce your email. That's
very strange wording.
Yeah. Well, at least they don't hesitate to contact them.
This is really strange. We're not getting anything through from them. I wonder if their email server's down.
Do you have a Gmail or something like that?
I can try a Gmail. Yeah. The problem is, yeah. Let me just see. Make sure I can go to my Gmail. Take this over here. Okay, let's give it a go with Gmail, shall we?
Sure. Codebase Alpha. One, 2, 3, 4, 5, 6, 7, 8, 9. That's the password, I guess.
Now we got this one, 44 times 35.
140 plus 1,540. Ah!
Well done.
I done my part for tonight. Please check that you enter and confirm. Maybe.
Don't think I managed to line them up.
It's not supposed to be easy, but at
least... I've got something from ShaderToy straight away now.
Have a Gmail direct line.
Yeah, interesting that.
Maybe it's your postmaster that spams. Oh, ShaderToy. Yeah. That's a time sink for employees. We need to stop that.
It could be.
So now you can click new. And now you see it looks different. Then we take the source code you created.
Yeah, let's go and grab that. There we go.
And then you write the name, Codebase Alpha number 1. I don't know what is the name of your shader. And you add some tags. I would say 2D, comma weird. I don't know. It's not important. I don't really care about these things. And you write a description. That's a first shader on Codebase Alpha stream on Twitch. Should copy paste your link here, I think. Yeah, exactly right. That's that.
Yeah. There we go.
When you're done, you click submit.
So make it public, do we?
Yeah, public API.
Public API.
Yes.
And there we go.
So, can you share that link with me in our thing code share, and I can see if it works.
Sure will. There we go. If anyone in chat, feel free to do the same.
Yeah, copy paste it in chat.
The ShaderToys come through on Outlook now. Isn't that typical? I think I'll okay that one as well.
Yeah.
So we got to.
But it works for me, right? So I can go in here. I can click it. I can like it. Dink.
Hey, we got a like.
Yeah. So. What's also there is a link here. It's hard to explain, but it looks like a V on the side next to a plus sign. Under shader to
that one there, yeah.
Yeah.
Share this shader, yeah.
Click that. Now here you get something you can sort of copy paste in your if you didn't want to do it all by yourself, like we did it,
right.
You can get an iframe with the ShaderToy stuff in it.
Okay.
And that's sometimes easier, but I kind of like to have my own stuff.
It's a bit last century iframes, isn't it?
Yeah. I sometimes mention iframes at work, like, oh, when I'm building the SO applications and like, yeah, now we wanted to bring in different components and blah, blah, they should interfere with each other, and I say, oh, iframes. I just look at me. Shut up. So, but I mean, it's possible. It's very simple to sort of, copy paste that into your web page.
Absolutely,
just do it. And you can evolve this thing and make it cooler, and I have a lot of shaders on my account, and most of them are not published because they are completely unfinished. But it's a cool way to sort of share stuff, I think, with other developers.
Yeah,
and people
absolutely.
What's very common on this site is that people look at what you've been doing. If they like what you're doing, what they do is they copy paste your code and create a new shader, tinker with it, and then publish it again. So in this site is very much like a collaborative effort. Most of the really cool shaders, they build on another shader. They thought this was cool, but then they made it more cool, and that most often built on something else. There's very few shaders that are completely written from scratch. It's a very collaborative site.
Yeah.
So usually the license are like they have a license that's usually Creative Commons 0, which is public domain. But always the license is like, it's very, the idea with this site is share your ideas and create something cool. Don't fight over intellectual property. That's not why we're here.
It's like little artistic community.
Sorry?
It's like little artistic community.
Yeah. And I mean, there are some shaders here that are amazing, and but most of the shaders are, developed, it's a collaborative effort. Anyway, so what have we achieved? We have created our own web page that we can do it. We also created our own ShaderToy, and we can share this with others, which is pretty cool, I think. Right?
Yeah, very cool.
Shall we discuss 3D?
3D, yes. Let's do that. That should be very interesting.
So this went faster than I thought it did, so I haven't really thought about it. But let's say we go back to Kodelife. Kodelife is easier and faster to work with.
Yeah.
I still think that it's pretty decent. What's calling it? But let's. Did you save the original one, like the simple circle, or shall we make it into a circle?
We've got a previous version of this, which would be.
It's easy to make it in a circle again.
Can we make it from scratch again?
Yeah, sure. We can make it from scratch.
Yeah,
sure.
Just so that we've got kind of a record of how we did that on the stream.
Yeah.
So new.
Yeah, new.
Over to fragment. Yeah.
If you stop the time.
Here we go.
So the first thing you do here, right, if you're going to draw a circle, is we create this distance function for a circle.
Yeah.
And that, if you remember, was quite simple. If you just, I basically just want to see the distance field here. So let's just create the simplest way possible. And in your main method,
yeah,
under the UV coordinates, right, you say float d equals length of UV.
So that's the length of the vector UV, yeah.
Yeah, minus 0.5. So now we created a function that at a distance 0.5 from Origo, this function d will be very close to 0, or it should be 0.
Yes.
At other points, it shows you the distance to the surface, or whatever we can, circumference of the circle. So the way we draw the colors is that we say if the d is less than 0, color is white. It almost kind of worked already.
Yeah.
Frag color equal WEC 3 parentheses 1. No, it should be vec4. Sorry, because it's
colors a four element vector. Yeah.
And then you said frac, and before else it's white or it's black. I mean.
Okay.
And then you remove the line 41, 42, and so on. So so when the distance is less than 0 to the circle, we paint it white, and we get this thing here.
Yeah.
Now, can I borrow the cursor?
Yep, it's all yours.
Yeah, and then at least I thought. No, I think.
Let me cancel control and then give you back.
Maybe.
Try again now.
Have we shared again?
Yeah.
I don't get it.
You not got control?
Try again. I have control, it says. Well, yes. Request control, I click here.
Okay, what we'll have to do here is I'll stop sharing my screen and then reshare it.
Okay. Turn off the computer and turn it on again.
Yeah, turn it on and off again. Off and on again, even.
You know, I live in Norway, and and I'm from Sweden, and there is a kind of a friendly. I don't know what you can say. It's like give and take, or what do you say? Like between Swedes and Norwegians.
Right.
You can imagine brotherly love, and they call the power off button at work for the Swede button. Like that's because that's what the Swedish people. When it doesn't work, they just turn it off and on again and don't think about it. But I take this as a nice thing, because 90 times it works. 90% of the times it works, right? So the Swedish guy, he reboots the machine. 15 seconds later, he's working. The Norwegian guy, they sit there and for 30 minutes read logs, and it still not work. And then they reboot machine because they couldn't stop things. So I'm like, this is good stuff. Anyway, so yeah, what I want to do is sort of to compensate.
Yes, for the resolution, yeah.
Now we get back to this. Oh, yeah. Have to switch the keyboard.
Yeah, so Mårten's obviously got a Scandinavian keyboard, but they've got to switch it to a British style keyboard, so it's going to be.
I learned last time where these buttons were, and now I forgot it.
It's not something you're going to remember because you're only going to need it for this stream. So
I used to start programming on a German keyboard actually in the good old days.
There we go. Nice circle. I'm going to just see if I can update the resolution.
Oh yeah, we should.
1920 by 1080.
Yeah, I understood that, Dragonite, that you were Norwegian from you recognizing that thing.
Oh, and Dragonite's Norwegian. Oh, we got two Scandinavians on the stream.
You're outnumbered, SMP.
Yeah, I am. Yeah.
So by changing this a little bit here, no, that was the wrong side. And the Swedish as well. Boy, this is.
Oh, we got a Swede as well. Welcome to the Code Base Alpha Scandinavian special.
Yes, exactly right. So what we did now is that we say when the distance to the surface to the circumference of the circle is less than 0.1, we paint it white. Otherwise than that. So then we can see, but we want to see the distance, sort of the distance field.
Yeah.
Get a feeling of that thing, because when we start talking about ray tracers, I think this is a good image to have. So then I'm just gonna. We wrote all this last time, so I'm gonna write it again.
Yeah, write it quickly. Yeah.
If I can remember how to do it, of course. Is it divided by 0.1. So I take the modulus here, and I take the nd equal, I divide by 0.1. So this is just taking the modulus of the distance, so it's always between 0.1. And then we basically do the same thing again, but we take abs of the modulus distance.
Yeah.
If that is less than 0.1.
So we colored in red and green, didn't we?
Yeah, that's what we want to do. So we need to start with something. So let's see how we can. No. I can do advanced stuff here. Click this button.
Hey, it worked. We can cut and paste.
It did work? Yeah, but
it worked, yeah.
It doesn't look like I was hoping to.
Yeah. So we have any trouble with the sharing over Teams? We're having trouble with the cut and paste operation, but it worked fine.
But I was expecting more circles here. Let's see if I sometimes just tinker with numbers, see what happens. No, that's also right. MD is the modulus of the distance, and if that is less than 0.1, something should come out, I think. What happens if I comment that thing out?
Let's go look at the code from last time, shall we? There we go. So that was what we were doing before.
It kind of looks the same, right?
Very similar.
But copy paste that code anyway.
That you were taking the absolute value there.
Ah, that could be it. Okay.
Okay,
Did we? But copy paste the whole code so we don't have to spend too much time on this thing here.
Yeah.
As fun as it is. And now we need this color thing here. So I can write that code that I'm able to do, I think. Wake 3 call equal wake 3 0, right? And then instead we initialize call. Now I know why. Now I know why it failed. Because this branch hits, right?
Yeah.
And that overrides whatever we did before. So that it all makes sense now.
Yeah.
But we learned that from rewriting the code. So
colon then 1. Yeah. There we are.
Good. So what can we see from this thing? Why did I want to see this thing here? And the reason is that when we start to implement ray marchers, and now I hope you can see my mouse cursor here.
Yeah.
How a ray marcher will work is that we have an eye. Now this is 3D, but we have to sort of, we start in 2D, but we have to visualize we are in 3D. We have the eye in this position here. And what we're going to do is that we're going to create a ray for each pixel. So we're going to draw a ray between each pixel and the eye. And then we create a ray that we're going to follow.
Right.
And what we want to determine with the ray marcher is when we hit the surface of something that we want to ray trace. And the way a ray marcher works, if we start here, and let's say the ray goes in this direction here. Now, what this distance function does, it tells us the distance here.
Yes.
This is the distance we get. But the ray is traveling this way. So, but what we do here is we will say is, give me the distance to the object. And what will happen is we get this distance here. But then we say, okay, this is an approximation of how far it is to the object. So let's go that distance. And then we end up perhaps here.
Right, yeah.
this the whole way. Then we ask again, what is the distance to the object? And then we get this distance here. But so we travel that again here perhaps. And then we ask again. So we start with a pretty big first step, and then we get closer and closer to the distance. We get smaller and smaller stuff. And then at some point we intersect the surface of the object.
Yes.
And then we found an intersection of the object, and now we know the position where we intersect the object, and that's good because then we know the distance to the object, and we can also compute what's very important when we talk about ray tracers and graphics in general is the normal. And I assume you SMB know what the normal is.
Yes, this is the perpendicular.
Yes. So we want to know. So the normal at this point for a circle is like it's perpendicular. It just points out. It's very simple for a circle. For a more complex object, it can be harder to answer, but it's perpendicular to the point where we hit with the ray. And the reason that this is important is that, let's say we want to do reflection in ray tracing. Well, then we find the point we intersect, we draw a normal, and then we can use a special function called reflect that allows us to create a reflection ray.
Right.
Then we start ray tracing that thing to see what did we reflect this point. In addition to do lighting, what will happen is we find a point here, we take the normal, and to create what is called diffuse lighting. Now, we will talk in more detail later, but we could call something called diffuse lighting. Then we need to compute the angle between, let's say, light surface here and the normal. If the light surface is directly above the surface, the diffuse light on that surface is the most intense. If it's perpendicular, it's no diffuse lighting. So this follows the cosine of the angle. And in order to determine that angle, we need to compute the normal. So the normal is super important.
Yeah.
So, and also for something called specular lighting, which is the diffuse lighting is like giving general shade. Specular lighting is sort of that's basically a reflection of the light.
Okay, right, yeah. Like a spotlight might be shining on something, yeah.
And it gives it a shiny feel to object. So the normal is what's so cool about distance function is that we can actually compute the normal using the distance function. So we only need the distance function, and then we can compute numeric using numeric approximation a normal function, and that's very good because the distance function can be very complex when we do fractals.
Yeah,
it can be very, very hard to say, okay, it's hard to even produce the distance function. Then what is the normal of the distance function? That can be even harder to compute. So the good news is we don't need to do that. We can actually compute it, and I think now this is going way back in my math thing, but the distance function is kind of like a field, and then there's something called the Dirac function, I think, for field theory.
Yes.
Where we derive the field function in each direction to know how fast it's sort of changing in each direction, and that's roughly what we're going to do. But we're not going to do that. We're just going to take this point here and move it ever so slightly in x direction to get the change of pace of the distance function. Because we move it with x, then we know how fast it changes in x direction, in y direction, and in z direction, and then we can compute, and then we take that vector we get from that, and from that we can compute the normal.
So those are your partial differentials of that point, that movement, isn't it? Yeah, okay.
It actually ends up there. So in this case, if you're standing here, and then the normal goes in this direction. Now, if we go here towards this direction, up in y direction, the distance to the surface is almost the same.
Yeah.
Because we're moving along the surface. Hey, Copperberry.
Hi, Copperberry, welcome.
But if we move in the x direction, then they change quite much.
Yeah.
So what will happen then is when we compute it, we know that x is much larger than the y change, and that means that the normal we point in the x direction, and likewise up here. So that's we show that function as well, but that's basically what we know. But if we have that thing, we can actually produce a ray tracing engine. Now, getting all this code right from start is a little bit trickery. It's not very hard code, but getting it right and get something to show on the screen can be a little tricky. So I'm going to share code with you, and then we can talk about how it works. How does that sound?
That sounds fine.
Yeah. So if you, I would like to keep this open. So can we, or at least, or can you take a snapshot of the picture? Like
yeah.
If you hit Control-0.
Well, I can do do this.
If you take Control-0, yeah, we can do that as well. That's fine.
Okay.
Because then we can go back to this picture and talk about it, because it's much simpler to, at least I think it's simpler to visualize 2D, 3D. And now I need to find some good example code.
Put it into Paint actually.
Ooh, I got a comment on my weird stuff. Nice job of suppressing the noise. That made my day. So
excellent.
Yeah, that makes me happy when I get the positive feedback on my shaders.
Absolutely.
Yeah. And of course, my day is ruined when I get no feedback. So
everyone in chat, go over to ShaderToy and make some positive feedback from Mårten's
completely
shaders.
Spontaneous. You really mean that, don't you?
Yeah, really.
Yeah. So I'm going to share with you so if you create a new project, I'm going to share with you a little bit of code that you can put in this new project. And this is just something, start with something that is very, very simple. Now, this is old code, so I would call this distance field now instead of distance estimator. But heck, what the heck? You put that under there, yes, correct. Blank. So, what is this we're looking at? This is, instead of doing this 2D, we're now doing it 3D. So we have an sdiff sphere function. So you remember you had this distance to a circle function.
Yeah.
Now we have distance to a sphere, and it looks identical because it's just a vector 3. Instead of take vector 2, take vector 3,
yeah.
and it takes values.
Yeah.
And then we have the distance estimator, which is the distance to the object. In this case, just a sphere, but it can be more complex than this. The distance to objects is this thing here. Okay, so it starts basically the same as what we did before. Now, what we're going to do now is we are going to implement the ray marching function. And the purpose of the ray marching function is to find the intersection. We're going to follow a ray because we're going through a ray in space, and we want to find when it intersects with the object or if it has missed it.
Right.
And it's actually, I would say, for most people, not very complex code. You need a little bit more than I gave you, but not much more. I'm copy-pasting from some code. So did you see what I put in code share?
Yeah.
Copy-paste that thing, and then we can talk about it.
Okay.
So, okay, what is this thing here? This is called ray marching. So we implement the ray marcher. Different ways to do ray tracing, but ray marcher or sphere tracing is what we're doing here. So but it follows this principle we talked about before, that we have a ray, and the RO is by convention called ray origin. Right. And most of the shaders that you look at the site use RO for ray origin. This is just something that is convention. So this is where the ray starts. This is the I position.
Yeah.
And then we have RD, which is the ray direction, the way we travel.
Okay.
So we point in this direction. This is a normalized vector, by the way. It's length is 1.
Yeah.
And then we implement the for loop here that says that we go from 0 to max ray marches. So because we don't want an infinite loop, so we have limited that to 32 steps, or no, to 128 steps. That's a lot. But what this thing does is that they say, okay, take the origin plus the direction multiplied by the distance traveled, that is t.
Yeah.
And what is the distance to the object?
Yeah.
If the distance is lower than the tolerance, this should probably be the absolute value, but what the heck?
We found it, yeah.
Yeah. Then we have an intersection.
Yeah.
Or we have it travel longer than max ray length, so we kind of missed it or whatever.
Yeah.
Then we break the loop. Otherwise, we add to t the distance to the object, because that is the shortest distance to the object. So we're going to travel again.
Yeah.
See if we are either inside the tolerance or we missed it. And then we return the distance traveled.
Okay.
Is this possible to understand?
Yep, that's very simple.
Yeah.
Understanding what it's going to do in terms of creating a 3D image is more difficult, but yeah, conceptually that's a very simple.
Yeah. So we're trying to sort of, we're following an array, and we try to sort of, see if we intersect the object. And not. Okay, and I'm going to find the next part of this thing, this magic function here. And I'm using names that are often used in the shaders, right? So
yeah.
These are names that are often used in the shaders. How does the distance function work? So the distance function, distance field function, gives you the distance to the object, and in this case, a sphere. So if you want to scroll up to that, we got a question in the chat.
Yeah, I've got that.
So let's see if I can explain it. So we have a sphere, and the distance to the sphere is given the position p in space. We compute the length to that position, and we take that minus r. And if the position p is on the surface on the sphere, i.e., it's on the distance r, then we have intersected the sphere. So actually, if you create an equation system saying st sphere equals 0, then you return all the points where that are on the sphere. Now, when we're outside the sphere, the distance will be positive, and when we're inside the sphere, it's going to be negative.
Yeah. So r is the radius of the sphere, basically, isn't it? And
yes.
in the normalized coordinates. So the normalized coordinates are plus and minus 1 in the x, y, and z directions.
And if you open again this picture we took before, it is 2D picture. Yeah. So this is the distance. We see the distance field here for the distance function of a circle, which is the 2D representation of the sphere. And the points where the distance is 0 is the white. Yes. And the points where it's positive is green. That's outside. And the points that is red is inside. That's negative. And it's the same thing for 3D. How is the length calculated? That is, I don't know if you remember that, but it's a Pythagoras theorem from school. X squared plus y squared plus z squared, and you take the square root of that, and that gives you the length of a vector.
You just need to go and revise your linear algebra, but yes, it's basically Pythagoras.
Yeah, but you don't need to. You can just think of if you have a distance, or if you have a point in space or a point in space, or a point on a piece of paper, and the length gives you the length in if you have the ruler. That is the concept.
Yeah, we get this nice length function anyway that in the GLSL, so we haven't really got to understand.
No, it does that. It happens, but it uses Pythagoras theorem under hood. I'm sure. Well, I'm not sure, but I'm pretty sure about that. So they probably have even a built-in function in the GLSL for this thing.
Yeah.
Anyway, I had some code coming. Oh yeah. So if you take this code that I gave you here and you put it in, this is called render, and you put it below the raymarch function.
Okay, let's have a look at this then.
The purpose of render is to call the raymarch function given this thing, and depending on the result, it's going to compute a color. I'm not sure render is such a good name really, but that is really, it's by convention is often called render when you look at shaders. So it's just I try to pick names. So we have a sky color here and we have a color. And what happens is that if T is less than ray length, it should really be tolerance, but whatever. That means we have intersected object. No, this is correct. T is the distance to the object, and if that is less than ray length means we missed.
You missed, yeah.
Yeah. So then in this case we just paint the color, whatever that is, and it's going to look very ugly.
Mm-hmm.
And otherwise we paint the sky color, which is another color. So this is going to look bad, but we start by this thing. But the purpose of the render is we raymarch, and depending on if we miss the object or not, we give it two different colors.
Yeah.
And usually when we look at raymarchers, this is where the magic happens in this kind of function, when you produce lighting and all these kind of things.
Yeah.
The raymarchers themselves, to find intersections, are usually quite the same. But here, there is a lot of trickery and craft, I would say. It's not so much math, it's more craft.
Yeah.
You learn some tricks how to make it look good, and then you experiment, and then it looks good, and you publish it, and you feel like a genius. You basically just you tried a lot of things, and then find a combination that looked fine, and then you're like, yeah, this is good, ship it.
Yeah.
And this is also the reason I like shaders, because I can tinker around and test things. And often it looks crap, but sometimes I hit the combination, looks great, and I'm like so happy about that. And then I put it up on ShaderToy. Usually when you create bugs in you write your business logic, it just crashes, and then suddenly it runs. But with shaders, it runs all the time. It just looks crap often. But sometimes something that doesn't work looks really amazing for some reason, and you publish that thing. So I like this sort of this model where it's always runnable, and it's not always doing what you want it to do, but sometimes it does something even better than you thought it would do.
Yeah, and you just follow your instincts, can't you? Once you find something, you can just carry on tinkering and refine it.
Yeah. So let's see now if I can find here. Yeah. I'm just looking and seeing that this is probably not really. Let's see. I think there is. This will not work exactly, but we can probably tinker with it till it works.
Okay.
So I share some more code, and this you should put in the main method.
Where do you want it to go? Just above Vec2 UV, or
remove. Actually, we should. Keep UV, but remove the frag color. And now it's complaining that then. Now we need to compensate the UV as well. So we have to write this resolution thing here. Actually, you can type Vec2P. Replace UV with P.
There we go.
And then you say P.x equals, this is the thing you learn by heart, never really understanding it. You multiply equal.
Yeah.
And then you go resolution.x divided by resolution.y. And that works, as far as I know. This is to compensate the resolution thing. Good. And then you set frag color equals frag color.
Is it going to be a Vec4 col?
Yeah, Vec4.
something like that.
Yes. Vec 4, not Vec 6.
Vec 6, essentially.
Cool.
There we go.
There we go. Okay. So this is probably one of the hardest part to get, but it's also one of the parts that never change, so to say. So what's happening here? Well, RO, that is the ray origin.
Yeah.
And that is the camera, that is the eye position. And from the ray origin, we have a position P. And from this position P, we want to create a array. So I think conceptually you can visualize this. You have a point P in space, a singular point. And then you have, in front of that point P, you have a square, a rectangular, representing the screen.
Yeah.
The input coordinate here, P here, points to the pixel on the screen, if you get what I mean.
Yes.
Then we draw a line through the point that represents our eye, through the pixel on the screen. And that is the ray direction. This is the direction we're going to follow. And this is what this magic with the vector does here.
Yeah.
It computes that that you're giving you that direction, and it does that by first finding a look. This is the direction we are looking at. So this is the direction we're looking at. But from that's not enough. We need also to sort of find the up direction, and that is this direction. And then we take the cross product to create a vector that is perpendicular.
Yeah.
To both the up vector and the vector we're traveling in, and then we get the three-dimensional space, and that we use to construct the yes, and that is used to construct the RD. But I usually can't figure this thing out when I think about it for like maybe half an hour or 50 minutes or 1 hour, depending on how I feel. But this thing never changes. The purpose of this thing here is just to produce the direction that we travel through to intersect. So I'm more like, I accepted this code.
Yeah.
I think I understood it at once, but now I'm like, yeah, whatever, it works. So that is my suggestion. It's okay, it works.
So we did mention cross products last time, and we talked about the right-hand rule when you get the perpendicular vectors. So either look back at that brief mention of the cross product, or just look up on the internet on Wiki. I'm sure Wikipedia's got a reasonable explanation of it.
Yeah, but you see a blue circle now on the screen.
It's actually a sphere, isn't it?
Yeah, it's actually a sphere. It just looks awful, right?
Yeah.
And the reason it looks awful, or looks like a circle, is because we actually find the intersection of the sphere, but we color each point the same color,
yeah,
and that make it look like a circle. What we want to do is change the color of the sphere depending on the light source, and use diffuse lighting. And so we don't have the same color over and over again.
Yeah.
Does that make sense?
It does, yeah. Obviously, because that's what happens in real life, isn't it? Is that even if it's the same, even if it's like a red ball, the actual our eye doesn't see the same color.
There's a shade to it, and then our brain constructs a 3D image.
Yeah.
In many ways, I think that we humans, we see 2D. We see a 3D projected onto a 2D eye.
Yeah, and then the brain does the work, yeah.
And brain, from the shading, reconstructs the objects as good as it can. So let's add lighting to this thing. But what we actually have array marchers here now. That's even though it looks crap, this is a big step forward, so to say. So we can add some diffuse lighting. But this way to ray march, this distant estimator, this is like it always appears in these examples on the on ShaderToy. So
this is like the core of it, isn't it? Yeah.
Yeah. So as I mentioned, something we need to compute is something called the normal. So I'm going to share a little bit of code with you here now again that computes the normal.
Okay.
Put it before the render function.
There we go.
So that looks, this is also a classic function. If you look into all these ShaderToy examples, this comes back over and over again. This is the way people do it. Now, what does this thing do? Well, we create this epsilon vector. Epsilon means a small number, if you remember that from school. And what it does here is it says, well, let's take the position. This is the position where we have intersected the sphere, and move a little bit in the x direction. And then take the same position and move the opposite direction in the x direction.
Right,
and then we
okay,
get this becomes the normal. This is a differential on the x-axis.
Yeah.
So this measures how fast the distance function changes in the x-axis. And then we do the same for y, and then we do the same for z. And then we normalize it. And now the vector is of length 1. And this is kind of like a derivative. Kind of. It's not really a derivative, but it points in the same direction as the derivative, I think.
Yeah.
And this then creates the normal. And using the normal, we can do amazing stuff. Because we can now shade the object according to that. So let's see now. I'm going to share another function with you, which is very, very small. But that is actually diffuse lighting function.
Okay.
So what this thing here is, diffuse lighting is, well, that's kind of what we normally see on objects, where like it's not a reflection, it's light that is sort of, it's reflected light, but it's not like a mirror. It's
yeah,
like
we're not looking at a chrome sphere here, are we? It's a sphere. It's like a ball or something like that.
Yeah. So, and the way this is done is like we computed a normal. That's very important. And then from this point, we're going to compute the direction to the light source.
Yeah.
And then this will return if the direction and the normal is pointing in the same direction. That means the light source is directly above the surface, kind of.
Yeah.
And then diffuse will return 1. If it's perpendicular, diffuse will return 0.
Yeah. So remember that when you got a dot product, the result is going to be a scalar number, and if the dot product is 0, then the two vectors are perpendicular to each other.
Yes, and if they are 1, they are
in
parallel.
the same direction. Yeah.
Is that right? So this is good, but we need a light source here. Let's see if I can find a good number for light source. Light position, perhaps this one. I'm going to share you. I share the light position. You can put that somewhere in the code.
Would you like that in the main function?
Yeah, we can put that. No, not in main. In the render function, because the render function is where we're going to compute the color. Yes. Now, the position light source is not the direction from the point to the light source. So inside the if statement, the if t is less than max rate, we're going to compute the direction from the point where we are to the light source.
Right.
Because that's what we needed to compute the diffuse lighting. And the way we do it is saying vec3 ld or whatever you want to call it, light direction equals oh yeah, we need to compute the position, right? And that's easy. So first you need to compute the position we are at, and that's very simple. You take vec3 pos.
And is this a separate line, yeah?
Above, right? pos equals RO, which is array origin,
Yeah.
plus the RT times RD. Not RT, T. So this is the intersection point. This is the point of pos is on the sphere if it worked, right?
Yeah.
So now the direction is between pos minus the light pos. Minus.
Oh, sorry.
Yeah. And then you need to normalize. This is something I always do. Normalize. I would just write it there. So normalize means that this vector has the length 3 or 4 depending on, but we want a vector that is always length 1 to make the math work.
Yeah.
And now we can compute the diffuse lighting by saying a float d float d equal diffuse, and I don't remember if the first parameter was the light direction or.
Can't remember how we spelled it. There was 2 F's.
Doofus.
That's why I'm. And that takes the normal vector and the light distance.
Yeah. No, you don't have the normal yet, but we can compute the normal. So put in nor and LD. Because we had this function. Well, I forgot the name of the function as well. What it was called. If you just go up.
Normal.
Normal, yeah. So we're going to compute the normal.
What is a vector?
Vector,
yeah.
Yes. There we go. So I don't know if this works, but let's just multiply d by color. Return color times multiply by d.
There we go, yeah.
Something happened.
Yeah. It's not the moon.
So what we can, now we see the shape, kind of, it's a sphere. The light source is probably behind it if we done it correctly, but we can see the shape of this object.
Yeah.
I will change the resolution to 1920 times something else because we can see it's a little bit jagged. Yeah. And also save this thing because Kodelife seldom crashes, but when it does, the code is gone.
So that'll be up on GitHub at the end of the stream.
So at Lightpost, put the minus sign in front of the 2. 968.
968. Oh, there we go.
Yep. So now it starts looking like a sphere, right?
It does.
So
very pretty sphere.
We traced a sphere. It's not amazing,
It's pretty amazing when you think that we're not in any way computing the surface of the sphere directly. We're actually, as you say, we're taking rays which are intersecting it using that distance function. So it's all kind of coming out of just that. That is defining the shape.
We actually have a mathematical definition of a sphere.
Yeah.
So let's reduce the. We can add much more to this, but let's reduce number of computations because we don't need 128 iterations for this thing. We can take a little bit less. So if you go up and you change this to 50, that should be enough. Yeah, and now we see if something else it gets weird.
Yeah.
Because it's it's kind of cool, but it gets weird. Yeah, 60. So now last time we talked about, so there are many things we don't have here that we need. Does that normal function compute extra arrays? No. Let's see, I'm trying to understand the question here. But the normal function calls the distance functions a couple extra times in order to measure the speed of change of the distance function in different axes, and then we normalize it, and that creates kind of derivative. Now, if you want to create mirrors or refraction, that is transparent objects where the ray is refracted through, then you need to, those rays you have to do them yourself, and it's further complicated in GLSL in that there is no recursion here. What you typically would do in a normal programming language like F# or C# is to say, okay, I'm going to compute a reflection ray. So what I'm going to do now, I'm going to create a ray and I'll do a recursive call to compute the next one, and then I have next reflection, I do a recursive call. There's no such luxury here. So it's totally doable, but it takes a little bit more effort. But the good thing about putting in that effort here is it's all real time, because everything here, this is retraced 6 times frames per second. But I'm going to suggest that we make this object a little bit more complex.
Yeah.
Just a little bit, and then we can start seeing the limitations of what we're looking at here. So in your distance estimate function, let's make 2 spheres. So I would say float D1 and float D2.
Shall I call them sphere 1 and sphere 2, shall I?
Yeah, or whatever. You call what you want. I like short function.
Yeah, I know you do, yeah.
Everybody understands D. That's the distance.
Okay, so we're going to take in P in here, yeah?
Yeah.
And what radius do we want?
0.1.
1.
Pick 1.
Yeah.
And P 0.5 perhaps.
Yeah.
And then you return sphere 1.
No difference. Good.
And you return sphere 2. Hopefully it's smaller. ST sphere. You have to. It's not ST sphere.
Yeah.
If you call it D1, it would be so simple.
It would have been simpler, yeah. No, it's half the size, yeah.
Yeah. Now, what we can do is you say, if you take the if you take the position there in line 32, you take P minus vec 3, and you say 1. Then we move this in space.
Yeah,
but let's just move it
across,
yeah. Let's just move it in x-axis here. So you say 1, 0, 0. Yeah. X-axis is apparently downwards.
Yeah,
that's interesting.
Let's just change that then.
Doesn't matter. It has to do with where the eye position is.
That's weird, isn't it?
Let me think about that. Let me try. Can I try?
Yeah, you can.
Oh yeah, one of these is likely. That's probably correct, but this is likely. You see, this is. This is the distance likely.
Oh right, yeah.
So like that, and if I say the stream disappeared, someone says it's not disappeared for me. I can see stuff.
We've got a few drop frames, but not many considering how long we've been on. So
maybe what happens if you refresh the stream there?
Yeah, try pressing F5. Here's now.
So now the question is, how do we see both of these objects at the same time?
So we have to do a max or a min or something like that, don't we? So we can.
Yes. So that is the magic of the distance function. In order to take the union of two shapes, arbitrarily shaped, we take the mean function of the two distances. So if you write the mean, return mean, sphere 1 and sphere 2. Have an extra parenthesis over there.
Oh, we've got well, we've almost got a water molecule, haven't we?
Yes, it's what's called it's a water molecule, but with one of them missing.
Yeah, it's a hydroxyl ion. Yeah.
It's I forgot. It's not acid. It's the other one.
It's hydroxyl. It's a hydroxyl.
So,
I used to be a chemist.
Yeah, but it looks like that. But the cool thing here is we actually created the union of these two shapes. Now, if you take the max function, it's going to be hard to see, I think. But if you take the max function instead of that, now what you have created is the intersection between these two shapes.
Yeah.
And I think personally that's amazing, because, like I said, I tinkered with triangles and these kind of things, and in order to take what's called intersection and all these kind of things, it's just such a pain.
Yeah. And
here we do it with mean and max function. It's just mind-boggling. Let's add rotation to all this thing here so we can see it rotating a little bit, so we can admire it from different views. And I'm trying to find, where do I find it here? Yeah, okay, so okay, I'm going to implement the function for you. You're going to recommend it. No, not recommend it, but you're going to recognize it. Can I take the screen?
Yep, it's all yours.
So this is the root function, which I always implement, and it's in out. Now I'm going to show you something which is actually quite cool by the whole, which is a little bit. When I realized you can do this, I thought this was quite cool. In what's it called in GLSL? No, that's wrong, and it's wrong again.
There we go.
And gonna compute the. I'm gonna apply. This is a 2D rotation. So we do it by taking cosine alpha float, and this is just something you learn.
Yeah.
It makes sense when you learn it, and then you forget it, and you just trust it. P equals back to P cosine.
What sign? What do you want? Multiplication sign?
Yeah, multiplication.
There you go.
Found it though. Yeah. Plus. Yikes! It's hard. You need a plus sign.
There you go.
Sine S multiplied by Py. And it's not done yet. Minus, no, yeah, sine multiplied by Px plus C multiplied by Py. Yeah, you can't blame keyboard though.
I can't blame it because that's just code-based alpha typing. That is.
Yeah. Okay. So what we're going to do now is going to rotate the where the eye is.
Yep.
And then I say rotate. I don't know what is correct here, but I'm going to take. Let's see. We start with this here. Let me take. let's run this and see what happens. I'm a little bit confused why the oh yeah, now I know why the color changed. Let's see. It looks a little bit. It looks like it jumps around in a weird way, right? I don't really get that. Some weird stuff is happening on the screen. It looks funny though.
Yeah.
But let's instead rotate.
That's better.
This looks better.
Yeah.
Okay, but the good thing about doing this thing here is now when we go back up and we take the intersection, replacing this with the max function, we can then see. We can then,
Okay, so I lost my cursor. So we want the max function, min function, yeah. That's diffuse. Sorry, where are we? We're in the sphere 1, sphere 2.
It's on top, very close to top.
Yeah.
So now we see the object here. These two spheres intersected. But now, if you put a minus sign in front of sphere 2.
Oh yes, that's right. Now we got the Death Star.
No, yeah, exactly. Now we have the sphere, and we have subtracted the sphere out of it.
Yeah.
Using max and min functions.
Amazing, isn't it?
I'm still amazed by the simplicity of this thing here. So this is a start, right?
It's a blueberry, yes. It looks like a blueberry, yes. I think the Death Star's more evocative, but it does look like a blueberry as well.
Yeah. So what we can do also, we can try to add this specular lighting and see if that sort of improves the fidelity a little bit here.
Yeah.
I have a specular lighting function, so I can share.
I'm sure you would.
Yeah, it's in the code share.
Right.
And the purpose of specular lighting is to make it look more like a bowling ball. Like there's a reflection element to it. It's not just diffuse lighting.
Yeah. So
if you compute the specular, and you need the normal, and you need the light direction, and you need the ray direction, you see here.
Yeah.
Because you see it takes the it actually reflects the light direction on the normal here. I don't know why it's minus. I think it's a bug here, but it doesn't matter. Let's see if it works.
Yeah.
So you use a special function called reflect that reflects the light. And I just try to see what happens. I think I don't understand why this minus sign is there. I think that's just wrong. But in addition to you compute float D equals diffuse, also float S, which is the specular lighting. And I immediately forgot how what order, but float S or something like that. So this will give you the value 1 when we looking kind of at the reflection of the light source. This is cheating, this kind of function, but that is the purpose, and it gives you 0 when there is no reflection in the flat. RD, I think it was.
RD, was it? RD. Yes, you're right. Of course, it's RD, direction of the ray. Yeah.
And I think it's as easy as adding S to color. You just take plus here.
No, there's a spotlight. Yeah.
Yeah. So if you start the animation again, we can see how it looks when it rotates. So now so what we see now is it moves differently because we're looking at the reflection here, and the reason it moves is because the eye is moving, but the light source is still. So we're looking at the reflection here. So let's see if can I borrow the screen again.
Yeah.
I think maybe. I don't understand these minus signs. I'm going to remove them. That's usually how I work. When things I don't understand, I remove them.
Yeah, see what happens.
And if it still seems to work, I think I did the right choice. Yeah, I don't get why that.
But now it's interesting. We're getting the reflection on the where it's been extracted as well, which is.
Yeah. But I think you agree that now it looks more like there's a shine to it.
Yeah.
And how many lines of code do we have here?
128.
So what we have done here is we've implemented a ray tracer that can ray trace very complex objects. Now we are lacking many features, but mainly in how we compute the lighting.
Yeah.
But we have implemented the diffuse lighting and the specular lighting, which can give us that. We're not going to see it yet, but I think we're going to try to make the object slightly more complex, and then we will see that we are lacking shadows.
Right.
And because now we don't really see it, because this object is not really shadowing itself, if you see what I mean.
Yeah.
But when we add a more complex object, we start thinking, wait a minute, why doesn't this cast shadow? It feels unnatural.
Right, yeah.
How do we do that in best way? Do you have any questions while I'm thinking?
No, it's pretty mind-blowing, really, to be honest. We seem to have moved on quite simply from the 2D, the
Yes.
kaleidoscope, to this. It seems quite a natural step.
Yes.
It doesn't seem difficult at all. I mean, there's some stuff in here which, as you say, there are kind of stock functions, and we just kind of accept what they do. But they're not difficult to understand. Perhaps the most difficult one would be the normalizer. To calculate in the normal, but
and that is kind of it always come back in the same way. It always looks the same.
Yeah.
The same way. I'm going to introduce another function now to you here. Two more, I think. So we can create. Let's see now here. Oh yeah, sorry.
Sorry, I'll take care of that.
Yeah. So this is just a helper function that I add. I'm going to find the rest of the function that you need. We're also going to create the box function. Yeah, okay. Look at that. Let's actually implement the box function as before. So we can have a box instead of
the sphere. Yeah.
Yeah. Let's take that.
So what we're building up here is a little bit of a toolkit where you can, folks on the stream can take this code and go and play with it and just change it.
Higher up, put it around the circle, sphere function, because we're going to need it in that one. But you're right, we're building up kind of a tool here, and sort of building up the function. And once again, it's pretty cool that everything happening in real time.
Yeah, and that's the great thing about this. Kodelife is fantastic, isn't it? You see, you really can, once you get something like this, you can just start fiddling with it and just changing it and see what happens.
Yeah.
Most of the time, as you say, it look rubbish, but one
but,
time out of 100, it's going to be.
And there's also many different tricks to make different colors. But let's scroll down, and we can add this box to this object. So if you go into the distance estimator function, we're now going to add the box to the spheres.
Okay.
So you make the float box. Equals st box, and you take p. We can start with that. And this take a vector, so you take vec3 1, and then you return instead of max these two. You comment this thing line out. We're going to keep it, but instead you take return box. And there's the box.
Wow, yeah.
So let's move that down. So you add what was it? Yeah, you add, you take P in SD box.
Yeah.
Not there, the SD box.
Yeah, SD box, yeah.
Minus vec3 0 1 0 1 0. Let's see what happens. That was wrong. Minus then.
Yeah, moved it down. Is that okay?
Yeah.
And
then you return instead of you. I would then just do float. Yeah, you take now return. You take mean around box, and you type comma, and you put in this max sphere 1, sphere 2, and we see what happens.
Ooh. Yeah.
Wow. Something happened as usual. So instead of -1, take -2.
Yeah, it's sitting on the plinth now.
Yeah. Let's make the box a little bit bigger. Take the box, make vec3 2. Let me experiment a bit. Is it okay?
Go on. Yeah.
It looks pretty cool, right? Like, once again, it wasn't at all what I expected or what I wanted, but it looked okay. So, and we'll go.
The lighting's working really well, isn't it? But it's not casting a shadow, as you say. So.
No, that is really. I mean, if you look at this, I think this is what bothers you at this point. Why is this not casting shadows? It should cast shadows, right?
Mm.
So the answer to that is, right, let's add shadows.
Okay.
Isn't that the natural thing?
I think so.
Missing shadows, we should add shadows. Now, shadows are usually expensive. And shadows certainly add expense. But and why is shadows expensive? Well, what we want to do here now is, if we are at the point here, we want to determine if I can travel from a point. Let's stop this thing here. If I can travel from a point unobstructed towards the light, if I don't go through the object itself. If I'm totally unobstructed, I'm not in shadow. But if I hit the object, then I'm in shade. And then I should color it differently. So the way we do this thing here is that we are using the distance estimate function. So we find the intersection point with the object, and then we find the direction towards the light from that point, and then we start ray marching in that direction and keeping track of if we ever pass through an object. And if we pass through an object, we are in shade. But if we miss an object, we're not in shade.
Yeah.
So that is the strategy. So we are going to reuse this distance estimate function again. And here is often a lot of tinkering and to make this good and to make it performant and blah blah blah. But I'm going to share a function here now.
Okay.
So if you look at here, didn't I share it? I did.
Yep,
yeah.
Soft shadow. Yeah.
And you put this above the render function. Now, often when we talk about these things, at least for me in the beginning, it was like, oh, this sounds concept. Okay, I understand it in concept, but how the hell does the code look? But actually, the code is not that hard either. It's not very elegant, but it's not that hard. So the way to read this is not the right word. It's wrongly written here. But it should be POS, not ray origin, because we start from an intersection point.
Let's change it, shall we?
And then you have to change their POS.
Yeah.
And then we should change RD to LD, because this is a light direction. So we start at the position where we intersected the object.
Yeah.
We computed the direction towards the light. We have a minimum starting point. That is because this is a, you know, yeah, if it's 0, 0.1, it looks good in this particular object.
Yes,
so,
yeah, okay. So it's a fudge factor, like.
Yeah, and K is how soft the shadows will be. So soft shadows are even harder usually than sharp shadows. But with ray marshals, actually, soft shadows is not so hard. This is an approximation. Well, soft shadows comes from that the light source is not a single point.
Yeah. Light
source is actually a sphere or spread out. But that's hard to do.
Mm-hmm.
So what we do in ray marshals often is that we sheet stuff. So what this thing does, this function, is that we iterate a few times, we compute the distance towards the object, and then we see, we kind of measure how close we are to the distance. And the closer we pass to an object, the stronger
the shadow,
it's going to be. If we're very far from an object, the shadow is going to be quite sort of, you know, non-shadow. So this has no physical meaning really. It's like making the objects kind of fuzzy instead of the light source being fuzzy.
Yeah.
But it's going to look okay. And then we travel in this direction, and we always travel this thing here. So this is just pure. Often what you do here is you tweak this to make it look good and to make it performant. So we are just going to take this thing here.
Yeah.
So let's call this shadow function here from where we compute the what's called the specular lighting after that one.
A new function, yeah.
Not here, but in the function.
In the
where
function,
we call
okay.
Not here. In the render function.
In the render function, okay. And we call specular here, yeah.
Yeah.
After that?
Yeah, sounds good.
Okay. So what does this return? This soft shadow returns a float.
I forgot if it's one means if it's in shade or it's not, but we will see what will happen.
Okay. Alright, so what do we need to pass into the soft shadow? We need to pass pos.
Yeah. I'm gonna look at what I usually pass into this function.
And then there was the light direction, wasn't there?
Yeah.
Then there was our min t.
It's 0.01, something like that. Sorry. And 16, I think is the number. And then I think if you put a parenthesis around the color, including the specular, and you multiply this by SC, let's see what happens.
Ooh.
Look at that.
We got a shadow.
Isn't that a shadow?
It is a shadow.
It is a shadow. Let's animate this.
Oh. Wow.
Isn't this pretty cool though?
It is amazing. And still we're not even 160 lines of code.
Yeah. So we implemented ray tracing with shadows. And you see, yeah. Isn't this is what I always dreamt about when I was a teenager, to be able to do this real time. The reason it's because it's the specular is not invisible. You're correct that it should be. The reason is if you scroll up here, SMB, is because the shadow is between, they clamp it. So if it said 25 there, it said 0 instead of 25. I think it should be. Now it's get very, very dark. So this is an approximation. I think it looks like, we know it's a little bit, it's fixable, but let's put it back to 25. Because then it's not so dark. Okay. So we have shadow. Shall we make this object a little bit more complex?
Yeah.
So now something something that's quite cool, I think, is well, how complex should we make it? Wow, we can start with not extremely complex. Now, do you remember this site? No, you probably not, but I'm going to share a link with you. A really cool site. Oh no! Oh, this is what we're going to do. I think this is going to blow your mind.
It's already pretty mind blowing, but we'll take a little bit more, can't we?
Yeah. This is how people think you're a wizard, and you haven't really worked that hard. That's what I like. I don't like working hard and people think, so what? I like to do a little bit of effort and people think I'm a god. It's just much better if it does like that. So I'm going to find sorry, I'm looking for a function which is a very cool function. Oh yeah, here it is.
Double blown, yeah, dragon eye, yeah. Both frontal lobes blown to pieces.
This is a cool function. This function by itself doesn't look that amazing, but you got to see. Well, I will do some experimentation. So if you look at what I shared here,
yeah, it doesn't look mind blowing, but let's have a look. Let's pop it into. Where would you like this to live?
Put it above the difference estimator. And then I'm going to write some code, I think, and sort of, hopefully. So you stop the animation. Yeah. So now, instead of this thing here, I'm going to do. No, not minus. There we go. Maybe it was good with 0.5. 0.75.
Yeah.
And then, okay. Plus sign, where are you?
I'll get it for you. There you go.
Sign.
Ooh.
Time. Well, no, it's not time. It's
just time. Yeah.
So let's animate this. Yeah, we can probably stop the rotation so we can see the animation more. So let's scroll down here. Where did we rotate this thing here? We said 1, 0. 0 is pretty good, right?
Yep.
1, 3. And run it.
It's oscillating backwards and forwards and penetrating the sphere. Yes.
Now, I think if I'm doing this correctly, you will be impressed. That's my goal.
I'm already impressed.
But I think this is.
You need Esmin in there, okay.
See what happens?
Yeah. Oh.
Isn't that impressive?
It is very impressive, yes.
So now it's soft.
Soft collision.
The multiplication sign.
Oh, I like that. Multiplication again. There you go.
Take a little bit slower. Let's multiply this by 0.3. So what happened there?
I love it.
We can make it even more.
I like deformation. It's very good.
So I saw this.
There's gravity there. It's collision of two planets, isn't it?
Kind of, right?
Yeah.
Now, hit Control 0. So let's say you have the mental model of triangles. Also see that the shadows, does the shadow work?
Yeah, it is, yeah.
Yeah. Let's say you have the metaballs, exactly right. Let's say you have the mental model of triangles. And you're thinking, oh, this is a fair and built up by triangles. And then you see this thing, at least I thought that, and like, how do you do it? I mean, it's just because all these triangles have to sort of interact with each other and sort of copy. It's just, it hurt my mind.
Yeah, not a triangle in sight in here, is there?
Yeah. So my mind hurt, and I couldn't realize how they're doing it. And I was like super impressed when I saw these things. Now, if you take Control 0 here, so you get back. What S-mean does is that when these two values are far apart, they return either A or B. But when they get closer to each other,
yeah,
they return kind of an exponential combination. So instead of the function going like that, it becomes like
curve,
that.
yeah.
So it's actually a very simple function, extremely simple function, but it gives you this result, which is, in my head, mind-boggling. There are actually some pretty cool variants of this thing, but I mean, this is good enough for a demo in the 1990s.
Absolutely.
So that's what we can do. Let's stop the animation. We can write the for loop here. X equals 0. X less than 1. This is hard. Plus again, I don't forget where it is. And now I'm going to call it D, whatever, even if you disagree. But
okay, you can go it wherever you want to.
Yeah. Copy this line here. Okay. Paste. Take this thing here. No, wrong button. I'm going to create something which can, I hope, look quite cool again. But I mean, I think you agree that it looked kind of cool, but
It looks
at the
very
same
cool.
time, I think you understood what we were doing, because we didn't really do that much.
No.
We did something very small that happened to look quite cool. I think I got this.
Don't start back through, do you?
No, I got it. I got it. I was just having to off there, and then we go minus off, like so. What happens if we change? If we animate this a little bit? Yeah, good. And then we go. Oh yeah. Box. Difficult when a keyboard shortcut doesn't work.
Yes, you rely on them so much.
D. Paste. What I'm going to do now is D equals. So instead of doing this a single one, what I'm rewriting now is to use a loop.
Yeah.
Instead. And sphere. And what is it complaining about now? Oh yeah. Oh yeah, because we have a 0 iteration.
Yeah, 0 there, yeah.
Okay.
That's the one, yeah.
But now we can make 2, but in order to make 2, we should make it a little bit more interesting. So what we can do now is take this off, and we rotate the XZ direction by X.
Okay.
Now this is, yeah. Let's see what happens if we take 2 balls now. Yes. And we don't want them to sort of, be completely in sync. So therefore we add plus sign.
Again.
And of course,
we just multiply them up.
add change to 5. Well,
it's astonishing. It's a piece of modern art. Wonderful. And yeah, we've done virtually no coding. And I like the way this bottom sphere is actually hitting the outside of the screen as well.
So, and all the shadows and everything kind of works.
Yeah.
So that's the power of ray mortars. It's actually, you can do weird stuff like this, and it's actually quite robust to manhandling the distance functions in this way.
Yeah, I mean, yeah, it's just pull it back. All we did was define 3 points in space, isn't it? Yeah.
This thing is the same thing. It returns the distance to the object.
Mm.
And then using these distance functions, we're computing the normals and all these kind of things. And it can handle this kind of, I don't know, gel-like object. And it looks quite good, I think.
It looks incredible.
And if you look at the amount of code we've written,
we've got 170 lines.
I mean, at work I can write 1,000 lines of code and nothing cool happen.
Yeah, I know that feeling.
Yeah, you have to write it, and here you write maybe like 100 lines of code and 150 lines of code, and people think you're a genius. But to be honest, what have we done here? It's not, when we've done it step by step. I mean, I don't think even the math is mind blowing here.
Well, we've been doing this part less than 2 hours, because we spent the first half hour, 35 minutes with the ShaderToy. So less than 2 hours, going very, very slowly.
Yes, and this you could put in your web page as well.
Mm. We
have to make it compatible with ShaderToy, but this is totally doable in a web page. So that's a start to do some pretty cool stuff.
It's astonishing. I'm really, really impressed.
Shall we review the code again to see where is the magic happening? Why is this thing even working? So if you start from the top, we created some helper functions here, right? We created this sphere function. That's easy to understand. And the box function, that's kind of an advanced version of our box function we made last time.
Yeah.
Using a max function. It's produce a box. It looks a little bit weird, but it's not. It's kind of straightforward how it works. And then we create this rotation function that allows us to apply rotations to objects, but it basically applies a 2D rotation.
Yeah.
Now, what's really cool about this thing is I want to point this out because I forgot to point it out before, and this is something you can do here. Is we have this is a 3D vector, but we pass in
2D,
the XZ coordinates, XZ part of the coordinates. We do the Swiss operator here, and this is passed to in-out vector 2. So this becomes a vector 2. We modify it, and because it's in-out, it's written back into this part as well.
Yeah, that's right.
It's quite powerful. It's quite cool that you can do this, I think. And this is a comment from Irmsna. Yes, I mean, if you think about how many floating point operations we're doing right now, we are above 30 billion floating point operations at least per second.
And this is the power of your GPU, isn't it? So
it's insane what you can do with the GPU. It's really ridiculous, the amount of performance available.
No, I do have a fairly powerful GPU in this PC, but I mean, as you say, some of these things you can do on mobile phones, can't you? So
yeah, this probably can handle mobile phone. You have to think a little bit on this soft shadow function, but I think it's doable on most iPhones and Android, or the top level ones. But they are quite powerful, actually, the cell phones.
Oh yeah, absolutely.
And then we create this smin function, which is a soft min function, which returns the minimum function of A and B if they're far apart, but if they're close, it creates some kind of soft transition between A and B. Okay?
Yeah.
And then we create a distance estimate function. And the purpose of distance estimate function, this is a distance field. The only thing this does is, given a position P, return the distance to the object. And the object we're looking on is all these spheres and this thing on the bottom, this box here. It returns from a position in space the distance. That's its purpose.
Yeah.
And because of this, it's very simple. It's possible to build up fractals using distance estimate function. And then these ray tracers works. But this is the only thing it does. Then we implemented a ray marching function that given a position where the eye is and a direction that we travel along.
Yeah. And
then we try to determine, are we intersecting the object we're looking at the screen? And the way we do that is we check if the distance to the object is less than a certain tolerance. That's a number we pick, 0.1.
Yeah.
We can change it, see what happens. Or we have traveled further than the max ray length, which is 32 here. That means we missed it and hit the sky, which is boring, sort of, gray. But if you look at the code here, it's not like it's mind-blowing. It's a for loop.
Yeah.
And then we take the distance, and then we travel that distance towards the object in the hope we're going to hit it. And that's it, really. That's the ray tracing function. The normal function is a little bit more. That's maybe the most mathy function in this whole thing.
Yeah.
But the good thing about this normal function is that this is the same for everyone. Almost everyone does this way. And what we do is we use the distance estimate function. So we have found the position P. This is a position on the object. And then we nudge the distance estimate function in X and Y and Z. And nor X is then how fast the distance function changes in X direction, how fast it changes in the Y direction, nor Z direction. And then that becomes the normal. That becomes the kind of estimate of a derivation. And that gives us the normal. The specular function, Then we have some helper functions here.
Yeah.
the specular function given the normal. Once again, this is the reason we compute the normal. We need the normal in order to compute the specular light, and to the light direction. What this function does here is that it tries to see if the reflected ray. So what we do is we reflect the light direction to the normal. We could do the RD, it doesn't matter this direction, but we reflect the light to the normal, and we try to see if the ray we are looking at comes close. They lie sort of, in parallel. So we take the dot product, and if they do, we kind of looking at the light. This is kind of how it works, the reflection. The diffuse lighting, then we determine the direction between the light direction and normal, and that creates the diffuse lighting. But this is also normal function. This is just, specular lighting is cheating. This is called Phong shading, but this just has no physical. It has physical representation. But diffuse lighting actually has some physical representation by it. Soft shadow. The purpose here is to sort of find if we are at the point, and we wonder if I am at this point here, and I travel towards the light, do I intersect an object? And the way it does it is travels towards the light, and it sees if the distance becomes very short. And you actually see that the light that is a little bit of soft. You see
yes, there's a little penumbra, whatever you might call it, around there. Yes,
exactly right. And that is what handled by this function. And then finally, the render function here, and not finally, but almost done. The purpose of the render function is to compute the color, given the direction, the starting point and direction. And then we call the ray march. So we find the intersection. This point here is where we intersected the object. And then we compute the direction to the light. We compute the normal. We use this diffuse function to compute the diffuse lighting, the specular lighting, and the soft shadow. And then we just add it all together in one way. There are different ways of doing this. This is a very simple way of doing it, which looked kind of okay.
Yeah.
And finally, we have the main function. And the purpose of the main function is just to sort of set up the ray origin, compute the different, create kind of a three-dimensional space from the up vector, the direction we're looking at, and using cross product. It's also a little bit math-free, but it's kind of the only math we do. And then we have the ray direction, we have the origin direction, and then we use the render function to compute the color given the ray origin and ray direction, and that's it.
Okay, and that's the amazing thing. All the program does is for every pixel on the screen determine what color it is at any instant.
Yep.
The output is that color. That's all it is. The output.
This is almost like a console program. Give an input, the position, computes the color. But the thing about this, how it works in the pixel shader, this program is run for each pixel individually. It's actually quite interesting how fragment shader works. Once there are a lot of threads and a lot of sort of hardware threads. I will not bore you too much about this, but if you know about SIMD instructions, I sometimes troll about that on the stream.
You do,
talk about AVX. AVX allows us to do 8 multiplication that multiplies 8 pairs at once. But in order to do that with .NET and C++, we have to put in a lot of effort. And they have something called auto-vectorizer, but they work like crap, if I'm being honest. They're not very good. Now, shaders work a little bit differently. So we are actually, this function is called with 32 different pixels at the same time. So instead of doing pixels at a time, and do 32 pixels at the same time. In addition, there are lots of CPUs and also lots and lots of hyperthreads running on a GPU. So you can maybe imagine like 100,000 threads of execution running at the same time. That's amazing.
10,000 cores, as you say, yeah, easily.
Yeah. So there is a combination of massive, lots of cores, lots of hyperthreads, and lots of very wide SIMD instruction set. Gives this amazing performance. But something to consider for this thing here, now I got into the tangent here, is one thing that's quite interesting is that if statements, actually both branches are executed.
Yeah, I've heard this, yeah.
Because you get 32 pixels of input to your computer at the same time. For some of these pixels, this might be true. For some of them, it might be false. But it happens. This is an effective SIMD instruction. So it needs to execute both branches.
Yeah.
But then they use something called mask registers to make sure. I don't know exactly if this is SIMD how GP works, but you only keep the results that matters from the first if, and you throw the other way around. So you have to be a little bit careful about if statements, but that's quite cool. And you get it for free.
Amazing.
Okay, but before we get into a point where we sort of round off.
Yep. I seem to have lost the Kodelife menu here. Do you know how to get it back?
Which one?
The menu.
Yeah, that's the Alt key.
Oh, there we go. Thank you. I just wanted to save the latest version of it.
But I want to show you a ShaderToy shader now.
Okay.
To show you that, boy, this was a really good one. I just randomly looked at something. No, give me a few seconds. If you have some questions, you can show, or someone can shoot them at me.
Yeah, any questions in chat?
I'm trying to look for some good examples.
Yeah, it's very insightful. Almost starts to make sense. Yeah, so it bears some thinking about. And I think also looking at the code. So the code will be up on GitHub. I'll just put my GitHub into the chat. So you're obviously free to go and look at this code, take it away, do whatever you want with it. I'll also put the ShaderToy code up there, so that'll be there. But yeah, there's certain parts of this where you can just take it that it works and start playing with it, and then there was a site that Mårten showed us last time, where they had lots of these little snippet functions, like the S-min and things. You can grab those and just play around with them and see what happens.
Yes, I mean that's how I started. I started with this. I looked a little bit, I read a little bit on these things, and then I started experimenting. And screw all this reading. I want to try it myself.
Yeah.
And I looked at a lot of examples, because that's the way it works in these things. You cannot really come up with all tricks yourself. Not even the smartest guy on the site has done everything himself. He's kind of, everybody kind of, borrows from each other and sort of, and learn from each other. So I really recommend just trying things out and looking at what other people are doing. But what I want to give you is a way to understand these examples on the site. So let's see now if I shared the link with you here. So if you take the link here.
Yeah,
so this is a pretty cool one.
Yeah.
If you look at the source code here, I'm going to look at the top. The map function here is actually the distance estimate function.
Yes.
He uses a fractal here, which is called Apollyon. So you can change here from, we don't have to do it. But this is actually taking a position P in, returns the distance. It's called map. It's sometimes called a distance estimator, whatever. Here it's called map. This guy likes to call it map. Then we have the trace function. This is the array marching function. You recognize this for loop. He's looping here. He's calling the map function, get the distance.
Yeah.
He checks if it hits the tolerance or what. But this looks very much like our for loop.
Yeah.
And then we have calc normal. I guess you can assume what that does.
Yeah, looks very similar. I recognize that.
And then we have the render function, and this computes the color, and he does a lot of lighting, blah, 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 blah. It doesn't really matter. But the purpose of this function is given the array origin, here it goes again, given RD, and anim, I don't know, this is something just added to do animations. I don't know what that is. But you can recognize the code, I think, and start understand if you want to tinker around here, or if you want to copy things, how to do it. And then we have the main function. If you go scroll down, and he does anti-aliasing. We can ignore that. but that is what this means. He dot anti-alias to make it look cooler.
Right.
We have this Ray Origin, TA, I don't know what that is.
This is all very similar here, isn't it?
But it's kind of the same thing. Also, it's VR support. So if you have VR goggles, this works. So you can look at this thing. But so the point is here, you can actually, I hope from the example we did here, look at this code and start making sense of it. Do you agree?
I think you can, yes. I mean, we've got the building blocks, as you say, to understand what it does. I mean, there's some, obviously, as you say, there's some more complexity in here, but there's nothing in here that we haven't actually got in a kind of a basic form in our program. So he's doing things like taking the square root of colours and doing some strange things, but you know, that's presumably all these numbers he's got here. He's done that empirically. He's played around and got numbers that look good.
He tinkered with it, you know. It's not. I think most people here are not able to come up with this. Like, I mean, you after a while you learn, but it's like from experimentation. I shared another link with you. Do you want to share that?
Yeah. Oops.
I think if I succeeded.
There we go.
So this looks pretty cool.
Yes, it does. This is what Codebase Alpha looks like on the inside. It's a very complicated place.
Yeah. So, but once again, now this guy, he also has his textures here. This is texture here. He does some text 3D sampling. I don't know all these things here. He does a length and formula. He has a camera path. This is a really cool thing. We don't have to. Here, by the way, is the smean function. Mean function. Yeah. Recognize that. We've done that. We understand. This is the distance function. We get a Menger sponge distance function here. So this is given a position P, we get the distance to the object, which is a Menger sponge in this case. This is a special kind of fractal that always comes back. He does some tubing. I don't know what that is. He actually writes comment. Oh, here's this map function. Yeah, the same thing as the other guy talked about.
This is well commented, isn't it?
Yeah, calc normal. Seen that before.
Yeah.
We know that now. This is something called, I didn't talk about that, but it calls an ambient occlusion. I can explain it maybe next time.
Yeah.
It's not very complicated, but this is that a corner in a room is more shaded than if you go further out. This is called ambient occlusion. And this is a pure sheeting trick they're doing here. Very common, this one they're doing. It has no physical, but it looks okay. So that's why they're doing it, because it's quite cheap. And then there are some other things, but it's, as you said, quite well commented. And here he does everything in the main image here. This is Shane. This guy is awesome. Everything he does is brilliant. Often he does brilliant lighting, brilliant. You can see the high fidelity of this thing here. It's really amazing.
It is. It's astonishing.
It's typical Shane stuff. But what I want to hope I get across is that we have a map function, we have a calc normal function, we have some things that come back over and over again. That even though our simple example look kind of crappy compared to this, the structure is the same.
Yes.
Let me see if I can find another example to show you. One. And I spent a lot of time just looking at amazing shaders.
Yeah.
So that's what I do. Let me see now. Gist. Let me see if I can find it. Oh, this is also. I can show you. This is also one of my favorites. Maybe not the most advanced one, but I think it looks so nice. It has so high fidelity to it. So I share the link with you.
Yep, let's have a look at that. Well, if there's anyone in chat who doesn't follow the stream, it'd be great if you hit that follow button to help me out with my my follower goal. It would be appreciated. Oh, look at this! Wow.
Yeah.
Thank you very much.
So what I liked about this one when I first saw it was this metallic look to it, and how he achieved that. And so this skybox, he has created skybox, which is very useful. But so let's talk about what's the same as everything else. Can I scroll on?
Yep, you've got control.
Yeah.
Thank you very much for those follows, by the way.
Yeah, environment box. I think this is the skybox. Yeah, this is what I stole. This is what. So I'm going to show you how to do it. But this is what gives the sky behind. So given the ray direction, given the sun direction, on what that is, we get the color back, and this is what gives the sky color. And you see, we have reflections here of the sky in the object. And the thing that he has this giant white stuff up here is what gives this metallic look to it. The smin function, it never gets old.
Yes, there it is.
Then it does some quite advanced math stuff, but basically this is a recursive splitting of distant things. But here is the distance to the object. This is the map function equals the distance to object. And then it does called sphere intersect. Okay, this is not so important. Somewhere we have the loop. Some people like to do it sometimes more. Ray marching is ray marching 290 times. That's impressive. 290 times, boy. And then but this is the ray marching function that it founds. Then it normalize and find a color and all this kind of thing. But basically, we find the different structures here that we see in our code as well. With little different names, but things come back over and over again. I would say, with what we talked about tonight, if you manage to grasp that, you can understand 90% of the shaders on this side. Of course, they put in a lot of effort and it looks amazing, but the structure is there.
I wonder how they think them up. Because I mean, even kind of, so I say, it's as you say, it's like we did. We didn't start off wanting to have 6 small spheres intersecting with a large sphere with soft collisions, but that's what we ended up with. I guess this guy started off with a shiny sphere and just chopped bits out of it, and
many of these things, at least when I do it, I start with one thing, I want to do this, and then I end up on a completely different track because that's how it's. Okay. So last one. Sort of showing another thing you can do. I have so many examples. Like I said, I've been looking at so many shaders.
Oh, clouds.
So now you can see we can do clouds as well. Not only like these sharp objects, we can actually do fluffy things. And this works a little bit different than the normal ray marchers, because what we do here is but we do the same thing. We create a ray. And then we traverse through the ray. But instead of having a distance estimate function, we have a sort of a cloud density field.
Right.
If you see, where we compute how dense the cloud is. And then we kind of make the beam be more white, sort of less opaque, depending on the density. And then we step through this over and over again then we go through this object here. And this is generated using a special called FBM technique, which I don't know what it stands for, to create a cloud from this noise here.
Right, yeah.
But so this actually works a little bit different, but it's the same. Also, a lot of things that are the same. We are stepping through the space using this function here, and you see we have the map functions, but here it's more of a density field rather than distance field, because that makes sense here. But we have the render function, which produces the color, and we have the clouds, and blah blah blah, and the main image. And this is just 140 lines of code to produce, I think, pretty amazing.
Isn't it? Yeah.
So you can do a lot of stuff.
So thank you so much, Morten. That's absolutely amazing. So I don't know where we're going to take it next. Maybe some fractals next time. But look at this. It's just like what we can do in a few lines of code. Incredible.
I think what we should do, or we could do, is improve the lighting and add more sort of, we could add different materials, so there are different colors or different spheres.
Yeah, that'd be good. Yeah.
I mean, we are using very primitive things here. We can add ambient occlusion. There are things we can do to make both the object we're looking at more interesting, but also making it more sort of high fidelity, sort of things. So that's something we can do. I mean, the sky is the limit, really, of what you can do in these things here. It's like really, you can think as well if you want to. Like,
oh, we'll do. Yeah.
Where do you want to take the direction? And maybe we start in that direction, and then we end up doing something completely different.
And that's the joy of it, isn't it? So,
yeah. But I think we've done pretty good today.
We have.
This is if you saw this from the start, like this is what we're going to do today, I think maybe you would have thought, boy, this is going to be complicated.
But we went back to first principles again, didn't we? We drew a circle, we drew a distance field in 2D. And then just extrapolated from that into 3D. So that's
And then at some point we introduced the magic S-mean function and made this gelatinous.
Yeah, it's quite astonishing. It's a very simple little mathematical function. There's a few exponentials on the log at the end of it, and we get this amazing behavior. Yeah.
Yeah, I should show it to co-workers tomorrow. And
we'll do. Yes. Thank you, Dragon Eye. Thank you for the kind words. It's amazing, isn't it?
Yeah, I think it's pretty cool. Let's add a final rotation so we can rotate this and see how it looks when we rotate it. So we scroll down here, and instead of this thing here, we said that's too fast, right? Multiply by 0.2, perhaps. 0.2, yes. That's better, right?
Yeah.
Now I want to see it on the stream. How it looks. Right here. Yeah, there we go. It's not too bad.
No, it's fantastic. I mean, I just couldn't imagine we could have produced it in such a short time.
In real time.
Yeah, we've coded it not live, haven't we? So I mean, you've
and also this is not an animation we're looking at. It's actually happening.
Yeah, it's being calculated. This is what I say about the about Electric Alpha and the hyperspatial hype, is that they're not animations, they're not films. Nope. It's all calculations happening in real time now, so it's always different. Yeah.
Yep. Electric Alpha is like this inverted cloud, strange thing, and the hyperspace alpha is actually a Julia fractal, but it's texture mapped. And then we sort of tweak it a little bit. I think we've done pretty good today.
I think we've done fantastically well. So thank you so much for taking us through that. And we look forward to where we can take it next time. So thank you very much, everybody. Now, this stream, the video of this stream obviously is on Twitch for the next 60 days, but it will be up on YouTube after 24 hours have expired. So my YouTube is over here. It's posted in chat now, so do pop across there. Hit the subscribe button on YouTube and help me out with that. It's completely free to do so. The part one of this series, last time we looked, had 145 views, which is way more than anything else I've got on there. So thank you so much for everyone who's viewed that. Thank you once again for Mårten for a truly amazing stream to taking us through this. So thanks once again, Mårten. So anyway,
it's my pleasure.
Yeah.
I'm just transfixed by the amorphous balls running.
So anyway, to say that the next shader stream will plan to be next Monday. Mårten and I'll get together and work out what we're going to going to do. But I think we'll, as you suggest, we'll start off by trying to improve this this animation with some more techniques, and then see where we go from there. So I think what we'll do now is wrap the stream up. What I'll do is I'll find another streamer to go and raid. So let's pop it over to. So I just wanted to say thanks to Hexler for Kodelife. So this is Hexler's website. They are followers of the stream. So if there's anyone from Hexler happens to be in chat, thank you very much for following, and thanks for the product. It's great. So
really good.
Do go over to hexler.net and download Kodelife and have a play. So let's go over to Twitch and find someone to raid. I don't know if anyone's going to be around. Who have we got? Oh, we've got Source Scoot. Let's go to raid Source Scoot. That seems a reasonable thing to do. So do stay with us to pick up with Source Scoot. Otherwise, we will see you for more shaders next Monday, and I'm planning to stream on Wednesday where we do some more text adventure stuff. So do stay with us for the raid. If you have any emotes, then just spam chat with emotes when we hit Source Scoot's stream. So once again, thank you so much, and we'll see you next time.